but Ukraine, Poland, Croatia, and France. So when I was abroad, just in France, beginning of lecture was where from professor was, the city. So also I would like where I am. So we have Europe, everyone are from the Europe. We have here Poland. Poland is divided on several regions. One of these regions is Opole. Opole region is the smallest part of Poland, and Opole is the capital of this region. So it's our region with Opole in mean. Here, very close is Czech Republic. It is the main building of it was the main building of our university. Now it's the main building of, in Polish, Faculty of Mechanical Engineering, and I'm just here and in this building, nearly on the roof in this place. Exactly. But the lecture territory is in Tarnopol. So here's photo from Tarnopol, where is rector and also me several years ago. I have good days at this university.
Thank you for remember me.
Yes, I remember you. I remember all your team, and I remember very pleasure days when I spent in Tarnopol and Ukraine. Or I hope in future it will be possible to come back to your university. As you remember, he is Dean of Faculty of Mechanical Engineering, probably on the left, as I remember, and other.
Thank you. I invite you to our university.
Yeah, with pleasure, I will come back to you.
Thank you.
1 year, maybe 2 years. We'll see about epidemic. So we might start lecture. It is photo of me. It's lecture at my university. So I told something basic of our problems of scientific problem and geography and history. So you may say that many factors influence the fatigue lifetime. It is temperature, frequency, environment, surface quality, and very, very important type of loading. Because it depends, for example, you have normal stress, and this normal stress or strains are from, or for example, from bending. It's not the same stress. This influence can be complex. So temperature with frequency and temp loading. So this is very, very complicated. But I would like to say more about type of loading, not about multi-axial loading, because multi-axial loading, it must be a special lecture, maybe 2-3 hours to say more about multi-axial loading. So we want to say about how to do experiment in bending or torsion. It is very similar, but you will see on the end. A little history of fatigue, but also, of course, basic of this. There are 3 points which are important. It is published the first article on the fatigue. So he made a stand for testing conveyor chains used in mines in Klaushal in Germany. It was basic of this problem. In 1870, Weller summarized its work on railway axles. He concludes that the cyclic stress is more important than the maximum stress are introduced the concept of fatigue limit. And next, in 1910, Pasquin from France, he proposed a double logarithmic relationship for SN plots using the data of Weller. Here I may say that very often in literature, people write about Weller curve, but in practice it is Pasquin curve. and very often used in practice is Baskin curve. Well, in practice is 100 years only. So the most loaded fragments with different types of loads. It's very important. When we have push-pull, in every point on this section area, we may start with fracture. When we have torsion or rotating bending, we may obtain beginning of fracture outside of material on the surface. But when you have bending in the plane, you have in practice two critical points. So you may see that in push-pull or in bending, it's not the same. You may see in practice, bending in plane, you have two small spacements. In fact, I will say on the end, it is the new paper in International Vulnar Fatigue, which we write that bending is nearly the same as size effect. Here is example of fracture 10H NAP steel. It's from my PhD thesis. First photo is uniaxial loading, push-pull. Second is bending. And the last one is torsion of this steel. So when we see on the first two spacements, the fracture is very similar. Also, when you see across the section, it is similar. But the fatigue lifetime, no. And when you have, for example, with some angle, this angle is between 0 or 35 degrees. Of course, it depends also of kind of materials, aluminum, steel, brass, cast iron, ceramics, and etc. So also it's other very important area when we calculated this critical or fracture plane. For some authors it's the same, for other it's not the same. In my opinion, I'm sure that it's not the same. But it is very, very important. Here is photo cross section when you have initiation. For example, here you have initiation, point of initiation. Next, we have fatigue crack propagation. One line. Up we obtain fatigue area, and next this cross section is smaller, and after then it's very fast fracture. In practice is nearly the static fracture, or maybe dynamic fracture. But this region, this big region, it's no fatigue. It is after fatigue problem. Of course, fatigue crack propagation in fatigue is one problem, maybe initiation one problem, fatigue crack propagation, and static fast fracture is third problem. So fracture on the end, it is three problems. And I know that some of the students, some of the scientists are interested in first part, second or third. Sometimes they compare. Here is a cross of wood, but I would like to say every every year you obtain more and more in wood. It's the same. You obtain every site a little more of fatigue fracture plane. Usually, when you have uniaxial loading, push-pull, on the left you see the free surface, and the first stage, it's nearly 45 degrees is first stage, initiation, and next you have propagation across, but in practice, it is also 45 degrees usually, but 55 degrees up and down, up and down, up and down. So in practice also 45 degrees, but on the end we see line And here, some words about multiaxiality. For example, you see some element. This element always works with bending with torsion. And we may take moments from measurement, and we see that it's no proportionally, it's big problem how to calculate it, such problem in biaxial, in multiaxial fatigue. So I told multiaxial fatigue is a second problem, how to calculate it, especially when we have random loading. It is the same, it's other problem. Here we have bicycle, and we have tensometers put in several points. And we go by the bicycle by the road. It depends which part of bicycle we have. It's necessary to find the critical point of say bicycle, because you see that, for example, tensometer 7 is comparing other the time history of load up to, for example, tensometer 9. So it is necessary to do experiment for random loading. It's time history of such random loading. This is also from my PhD thesis. But to obtain some calculation, also it's very difficult, complicated, very aspects it is necessary to use to calculate it lifetime. We must have before this characteristic, fatigue characteristic. Cyclic loading, when you have obtained fatigue characteristic. It is cyclic, it is sinus, because usually we have sinus loading, because it's very easy to obtain on every hydraulic or electropulse machine. It depends, but it's very easy to obtain such characterization. Generally, we have amplitude, we have mean value, or you have maximum and minimum value. As we may see that basic loading, when you have sigma maximum is minus of sigma minimum. So in this time, we have mean value 0. It is basic. But we must know that very often for example, the mass of, for example, in the bridge, and very often we have influence of mean value. So it's necessary also to know how mean value influence on lifetime. It depends on materials, and it depends of how large is this mean value compared to amplitude value. So also it opens a new area for scientifics. But for example, we have problem in plane. So in practice, very often you have random loading. For example, it's such big machine. But sorry, I have in Polish, I didn't change it. But it's at the beginning we have very small. On the higher top, for example, 12 kilometers, we have very small change, but we have maximum of stress. And next, when the plane go down, you have obtained smaller at up to 0. So in practice, we calculated lifetime not for this random loading. What we see, minimum 0, maximum when the fly is on the higher position, and go down. So in practice, such one fly is one cycle. And very often in practice, we have some experimental lifetime or history of stress, strain, in practice load. But if it is possible, we see how you may do Because of this, we may see that in literature, very often we see cyclic loading or sum of some cyclic loadings. Here we have typical SN curve for brittle aluminum. We see that on the x-axis we have life cycle, the scale is logarithmic. In practice, in fatigue, this scale is always logarithmic scale. On the left, we have here stress of amplitude. Here we have linear relationship as in Weller, but very often is this basket equation. So we have made all lifetime divided for 4 regions. At the beginning, to, for example, 100 cycles. So in practice, we may calculate it as static, and it is enough to calculate it that such machines are not dangerous. Next region is low cycle fatigue. Where is maximum of low cycle fatigue? It's more than 10 power 4 cycles, sometimes less, sometimes more. In practice, low cycle fatigues when we have large plastic strain. But if plastic strain are larger than elastic strain, we may say that it's low cycle fatigue. But in this region, usually you must calculate it strain characteristics, not stress characteristics. Next region is high cycle fatigue. 2 million cycles, it depends on materials. In this region, we neglected plastic strain, and we may say that it's nearly only elastic strain, so we may calculate it by stress. I would like to say that when I have contact with some factories, they use very often only stresses. For engineer, typical engineer, stress is more easy to use compared to the strain. I've seen that sometimes in factories, they told that they measurement stress by tensometer. Of course, tensometer measurement strain. So they use strains and say it about stress because it's more easy for typical engineer. You may should use strains. Sometimes strain and stress is energy theory. I did many papers also in energy strain and strains calculation, also in multi-axial. It was my habitation. Last time I also come back to this because it is necessary to use also, I think, stress and strain. And next, the last region is nearly fatigue limit. It is the stress when we may use for all region, but we may remember that it is possible to use such strain. But for example, for aluminum alloy, this line go down and down and down, and now it's such stress when we may use that it will be not danger. So it is region, gigacycles, but this region is not so known because we make many days to do some experimental data. Of course, we may do high frequency, but we have used high frequency for experimental. We have problem, for example, with temperature. It's other problem in calculation and do experiment. So here, this is 2 curves, what I told. First curve is Weller curve, linear relationship between stress amplitude, and basking curve. 2 kinds of equation, but here we have logarithm of this amplitude. And here we may have, for example, a Weller curve high-sec fatigue F and fatigue leaves for 10 HNPA steel. We see that on one level we have many points and how to use in practice, because it is very difficult to say, because this line, it is only fit. And here from literature we see that we may find some percent of probability, but also here you have 1% that maybe will be catastrophe. So never we say in fatigue that we are sure that it will not be danger, but we must now decide, for example, 1% that it will be catastrophe. So we see that sometimes there are some catastrophes. So when we move to the left, danger. So we might decide, it is in my equation, we must decide where we may put this blue dashes line. It must be decided or by engineer or by some standards. Some standards may say that we might move on the left, for example, 97.5% for welding joints, for example. And others, sometimes specific machines may say how may move on the left. Here is Manson coffin baskin when you may use strain, so you might use Manson coffin baskin. So you may divide it strain amplitude by elastic and plastic. So this is such. Here is plastic region and elastic, and the sum of plastic and elastic is this line. You may say that we have big number of sides. We have the hysteresis loop is very small. When you have larger plastic strain, we have larger plastic hysteresis loop. How started this hysteresis loop? It started from 0, 0. Started, it's for example, it will be static. Go to the maximum value of stress, stop, and come back. And when we go on this point, we have this is plastic strain. So typical hysteresis loop, it looks as here on this equation. But it's necessary to say, okay, sometimes we have such comfortable material, but usually this hysteresis change. For example, here has the first side here, and every side the stress amplitude was less up to the fracture. So usually this hysteresis loop is no constant during the history of fatigue experiment. So we have loading program sinus of strain. So because of this, we have changing of stress. When we have softening materials down, the stresses go down as earlier. But there are some materials which are cyclic hardening, and every cycle, the stress amplitude on the right hand sometimes go down for cyclic softening, and hysteresis go up when this cyclic hardening. And on the end, we have relationship between stress and strain. First line, it is static or cyclic loading for ideal material, and it here is a function for this. But in practice, for the softening material, we really have this down line. It's function between strain amplitude of stress amplitude, or upper line for hardening material. In practice, more material are softening compared to hardening, but there are some materials that are hardening material. loading, the changings for, you have changing of stress and strain. Solid line is stress, dashes line is strain. It is possible to measurement. It is very easy, well, maybe not very, but it's easy. You may use it in push-pull experiment where we make measurement force, so we have stress, and measurement strain, and we have this. I would like to say that this hysteresis loop is standard. It's possible to do it by changing of cyclic amplitude, but also it's possible we have random loading, as you've seen earlier. This was made with comparison with Professor Billy from Bratislava. From time history, take amplitude of strain and stress. If only from one spaceman, we obtain relationship between strain amplitude and stress amplitude. And this constant amplitude is dash line and dashes is for random amplitude. The difference between these two possibilities is very small, but when you use constant amplitude, you may use, for example, 10 or 20 spacemen. But when you use random loading, you may use only one spaceman. It was published in Ukrainian material science paper. And here we obtain experiment for aluminum. We did is fire cycle. You have seen that it's a little upper, next size 201. So it's hardening material, this aluminum hardening material. But the last cycle, you see that is go down, the stress is 0 or push, but in pull you obtain. During this time, we see that during the time history, it depends of strain amplitude, the stress amplitude change. When the strain amplitude is small, for 0.5, the stress amplitude is nearly the same. When we increase amplitude of strain, the stress is decreased very much. For example, you see 1.2, the stress amplitude decrease in all lifetime. And here we have the damage degree. The plastic part are smaller every degree, but the stress is high. It's typical for hardening materials. And also you may use parameters of Mansour-Coffin-Baskin equation. On the left is C, here is epsilon for this aluminum alloy, of course, and other parameters of this equation, B and sigma. So I thought that up to this point, maybe it's not very easy, but it's very known. Of course, it is possible to use some new influence, new equation, but we go strain and stress. But gradient, I would like to talk gradient in without node, because gradient, of course, is also in push-pull where you have node. But I would like to say about gradient, which we have from bending region, because you must remember that this changing of strain is linear, but because of such changing of strain, we have stress such equation. It depends of materials. So when we have moment, because in these points we have usually moment, it is necessary to find how to calculate it, stress and strain distribution across the section. So torsion stress strength gradient. For our experimental stand, we have such typical spacement, Diabolo spacement, and we made many experiments which were published in many journals. So we have, when we use computer analysis, we may see that stresses across the fracture for bending is here, for torsion is here. Everyone knows how to do such a calculation. So you may go now to dynamic bending and torsion stand. Typical our stand. We have several types of this stand because we did some changing to do better calculation, better measurement, special materials, and others. What we have here? Here is electromotor drive. It is rotated in constant frequency. Here we have heat with clamp of spacement holder. Here is spacement holder, and here is very small spacement. Spacement is along of the spacement is, as you thought, yes, so I come back, 90 millimeters. So very small. Such small spacement. It's and here is rotating disc. It is very important. It's rotating disc with ambulance weighted harmonic oscillatory. We change mass or angle between this mass, and we have forces in this direction. The arm of this here is 200 millimeters up to cross section of this spacement. Also, we have spring actuator. This spring you may use, but not every time you use, when we have obtained mean value other than 0. So in this time, we may use this spring to put some mean value of moment. So here we have some forces multiplied by 200 millimeters. We have here moment. Here is photo on such spacement. It is stopped during work. Here is spacement. Here it was copper. The last experiment made by me and my team. I will say later, but here also you have spring. And next, here it's possible to rotate this, and we may, if we it rotate, we obtain here on this spacement moment, but in this position we have torsion. We may rotate up to bending and also bending with slides. We will see how to do. Here is other photo, other stand. Here we may see that this climb is a little other because we may see all spacement here from up, and we may do photo to see propagation and others. But it is very new construction. The basic is the same, but we change a little special elements. Here is, for example, when the fracture is crushed and we are at home, for example, because it works every day and night, we have big moved here and it will stop this machine. that we may work every day, because 8 hours during the day is too small, because when we start experiment, we must have every hours to work with this. This is overview of this fatigue stand. I hope that we start the film, how it works. You will see. Oh, we will see the spaceman climb. But now this machine doesn't work. As I told, it is possible to move this rotating element to obtain only torsion on the right, only bending, and every position between bending and torsion, we may obtain bending with torsion divided total moment for these two parts. We change angle, we obtain biaxially, multi-axial fatigue bending with torsion. Oh, here we see now it is position of bending. We see how it works. It's no very big noise. And now it's position of torsion, and on this you may see its torsion. Of course, when we put position of possibility to experimental data, it's necessary to stop every crew. We come back to bending of this machine. You see the quality of this machine. It's not very clean. You see the surface, but in practice it works many days, many years. Sometimes it's necessary to clean, but we work many days on this spaceman. And here is photo for bending, position of bending with torsion, and now we have pure torsion. What position with spaceman, now we have only torsion. And also here you have position of bending. You have you see here it's flat, no circle experiment. Here probably it was platters, but in such a way, of course, you may use only for bending. Characteristic of bending these platters is probably aluminium with titan, sometimes aluminium with steel, titan, coppers. Such experiment we also do for big factory in Opole, Expromet, which prepare such elements for also for electricity, power station, chemical institution, and others. And here maybe you will see film how you may see how it will rotate, jump, forces, and moment. And we have now pure torsion here on this spaceman. So as you see that this every elements which are in this stand is made in our university. Maybe springs also are on the factory. Every element are made by us. Of course, electrical engine was bought, but it's very easy, and it's also very easy to use to do experiment. Also, students, I don't like to no PhD, but regular students also do some experiment degree of such experiment. And here is also photos which we may see the rotating part is here. Here is this mass, and we're changing mass. It was the first version. Now you may rotate on this position to move and changing the difference between upper and down mass. Last time, at the beginning, when I started my job, it was we had several times of mass. We complex this mass, and it was possible to obtain other forces, so other moments. And here you see this mass, and we see here every time we must control which moment we obtain. This first position we put, but after them we may check what moment we obtain directly, exactly at our stand in our experiment. And here is the control elements. Also, every is made by our colleagues. On the left side is I don't know in English, sterownik in Polish, we regular frequency, because it must work in frequency characteristic for every stand. Frequency on this stand is nearly 30 hertz. It depends, of course, of 5.5, sometimes a little more than 20. So we must check every stand after production, because it's production of our university. We must check to work with good stabilization. On the left side, also we calculated the number of sites. But we may do experiment to go here in this program. We may measurement moments, strains, frequency at many deflection and other to put moment. So it's a big program, computer program. This computer program is made by co-authors of the presentation of today, Roland Pawliczek. Our program is made by our department. And we see it's all electronics of this machine, very, very easy. And this box on the left, as I told, is also made by our university, but Department of Electricity, not our department. You may see how it looks, compare very close. It's pulpit configuration. You may put what kind of moments it should be, number of sites between each moment, and we may start of experiment, and you see that experiment started, for example, with moment 8 Newton meters, also deflection and other. As I know, I may use it, but I don't know every points of this because it's very complicated. Now it's possible to do also experiment more complicated. And here is photos of the spring. As I told, we may use, but it is necessary to use this spring. And after them, we obtain influence of mean value. And other stand is kinematic bending torsion stand. It's very, very new up to this day. Maybe you publish maybe 2, maybe 3 papers, because it's very new. Because before the moment was constant. Now, but this is the strain. So the box, as you see down, is nearly the same. characteristic is nearly the same, but you may see that here we haven't here any mass, but we have here changing of rotation, and here we the measurement, you may of course measurement moments, but the constant is strain. Here is the same box as before. Here also is program is prepared by our colleagues. Exactly, it was made by co-authors Andrzej Kurek. He knows this stand very well. And that is very close, but here we have, I don't know, it's no circle, the line it's moved a little. You may see, maybe on the film you may see how it works. You may see, and here you have big moments because the stand is big. This stand you may use also for low sake fatigue, because in moments when the moment was constant, experiment it's possible to use for high sake fatigue. But here you see częstotliwość, its frequency, its maximum frequency in this experiment is 5 Hz. Now this experiment was made not very large strain, but we may move to larger moment, larger strain, and after them we must use less frequency. So for this experiment, we also used 1 Hz. We did experiment for composite material, and for composite material we use 1 Hz because larger frequency may increase temperature, but temperature, for example, in steel, it's not very important up to 50 degrees, for example, but for composite material, plastic material, it will be big problem, so it's necessary to use smaller frequency. I put, you see that second time, works. Here, but of course, using this machine is very useful. This machine is small, the noise is not big compared to typical hydraulic push-pull stand. And usually, when you do experiment, you use in one time several stands. These kinematic stands, we have only 2. The earlier, when we was calculated moment, so we have about 12, maybe 20, I don't know exactly, because we change every day, and we did many experimental data. And now this is calculated stress and strain in such region. Here I put only for bending loading, but it's similar possibility to calculate it for torsion. Of course, other problem, it is calculation bending with torsion. But the main point of this stance, the first, was bending, because it's necessary to compare how influence bending and how influence uniaxial push-pull, and how this influence for fatigue materials. Is the same or not the same? And we know that distribution of strain is linear, as I told earlier, but now it's second time. Of course, it is strain. It means nearly 7%. more, it is not true, but more is no fatigue, it's nearly static or dynamic. We may calculate it that we have stress in every point when we calculated sum integral of these stresses across the section. We have moment, and I told earlier we know moment of experiment. And second, in every point of cross section we have calculation between strain, amplitude, and stress. When we have these three equations, we may calculate it when you have time history of moment. Oh, exactly. When cyclic, we have amplitude of moment, stress, and strains in every point. But of course, only it is necessary to use it, and we obtain it by numerical method. No other solution here. Analytical solution, it is impossible. But the program for this is very small, very easy. The same, very easy to do for torsion. It's the same moment, characterization, and the strain distribution. Other problem, it's when you have bending with torsion. In this time, we may use some multi-axial criteria. When I see in literature, you may use or Tresca or Hubel-Mises. Of course, other possibilities are is also possible, but it's necessary to find which kind of and we are very close to the end of this presentation. And I would like to say only two materials which we published last time in International Fatigue, and I would like to talk about bending when you have a nominal system. It's red points, it is nominal system. When we recalculate it, as I told earlier, we see that we have new down bending elastoplastic. So in this time we have amplitude of stress, but of course it is maximum stress on the surface. You may see that from 1 minor cycle for this material, 16 molybdenum 3, when you have nearly fatigue limit, elastoplastic in nominal value is the same. Why? Yes, it is very easy, because in this region, plastic strain is nearly zero. So if the plastic strain is zero, so elastoplastic and nominal is the same. When we increase moment, and so bending nominal, we have larger plastic strain. So in true, we have for example, for 1,000 sites, we have the stress less. For example, here down 160 up to 400, nearly 10% less for this team. And other experiment made by us, it is aluminum alloy 6082, and we see similar that bending nominal is red points, bending elastoplastic is green. It is nearly fatigue limit. It's nearly the same. It is here is 1 micron, but we go up to 300 sites. We see the difference between elastoplastic and nominal value, but here this decrease is smaller compared to steel. and many papers, many reports of some scientific from all the world, also earlier papers in my department. Usually people every analysis did in elastoplastic regime. But it's very, very interesting how to go to, sorry, it was used by nominal value, but it's very important to go to elastoplastic regime because it's more true. But in cyclic loading, as you see, it's not difficult. But when we go to random loading, it will be more complicated. And I think it is open for next analysis. And on the end, I would like to say we have C bending, these green points, but it is true stress. And we have tension compression, it's lower, always time for every materials. When I see in literature, bending is upper compared to push-pull. But as I told at the beginning this lecture, that bending is some kinds of small spacement. And we did experiments for small spacement, these red points, and see that is upper. So it's very interesting that for large number of sites, bending and push-pull is the same. But for small number of sites, bending is very close to the small spacement. I don't know why, but we obtain from experiment such results. Also, we do experiment for other materials, but it is necessary to have time. But we also did such calculation for aluminum alloy, bending, what I told earlier, these green points, tension compression, these blue points, you will see. But here I see that its material was not good because the changing on the left, on the right side is very large. It's not good. So it's very difficult to do analysis. And small spacement, this is red points. Bending, it's very close to each other. We don't know why, but we know that aluminium and steel is completely other. Aluminium is hardening, this steel is softening material, probably of this. So it's necessary to do other experimental. Of course, this small spacement was 3.5 millimeters only. It was necessary to use smaller diameters, but with the smaller diameters, we have problem with machine. So for the future, it will be problem of experiment, and next we may do such analysis. So use bending with torsion and analysis elastoplastic strength and strength, because this all strength, and I told when we have at our laboratory, is very, very good. It's cheap, no, small, no big noise, which is necessary to change every parts. We may change it in our laboratory with any problems, but it is problem with calculation, elastoplastic stress and strains, especially when you have BX18 and we have random loading. And we work in this subject, but I think we have more work every day. So thank you very much. Here is my email, my address or telephone, and his photo. University in Lvov. So also I had lecture in this place, and I had good time in Ukraine last year. Thank you very much.
Can this machine be used to test composite materials?
Yes, it is possible for composite material, but only this kinematic, as I told, because in this kinematic equipment, you may use small frequency. When used moments, it's impossible to use. We did first experimental for these composite materials, but only bending on the torsion. Now it's impossible to do experiment with bending with torsion because it's a problem with obtained good.
Okay.
I presented this paper last month in Crackpad conference, large conference was. I present it. It was made with cooperation with Andrzej Kuret and also my daughter Karina Głowacka. We made our calculation experiment. It is difficult because we did it first time, but I think it's possible. But it's necessary to have more information. Probably it also depends of what kind of composite materials you use.